Okay, good morning. Welcome to
SuperMath number 127a.
SuperMath127a. So yesterday I saw through a long chain of events, Patrick Honor posted a Richard Green essay that was about a proof that he saw on Cut the Knots website. So, and the proof was about infinitely many primes, and it was super cool. And we spent maybe 45 minutes going through it this morning.
Yeah.
We're going to try to do a second time through it now in a short movie, and it's good that we didn't go through it live because there were a couple parts of it that were harder than we were thinking.
Yeah.
But it's still really neat. But infinitely many primes. You said this morning, and I said this one will wait to go through. You said you already know a proof that there's infinitely many primes.
Yeah.
Do you remember how it goes?
Well, I think if you say there were finitely many primes,
Okay.
so 2, 3, 5, all the way up to p n,
Okay.
where n is an integer.
Whereas an integer. Okay, and that's it. There's just this. These are just the primes. That's it. There's no more primes.
So the way you can do it is you multiply 2 times 3 times 5 times times pn.
Okay. So you multiply them all together.
And then you add 1 to this.
All right.
So this isn't divisible by 2, it isn't divisible by 3, it isn't divisible by 5, isn't divisible by any of these up to pn.
How come? Why is it not? Why is this new product plus 1 not divisible by any of them?
Because it's 1 more than a multiple of 2, 1 more than a multiple of 3, 1 more than a multiple of 5, 1 more than a multiple of pn.
Okay. Great.
So this is a new prime. This number is a prime number.
Not necessarily.
Well, it's a new number that isn't divisible by any of the primes.
It's not divisible by any of these primes.
So there must be another prime.
But yeah, that's right. There's something called the fundamental theorem of arithmetic that says all integers can be factored into primes. This is an integer.
And you can't factor it into these primes.
Can't factor it into those primes. So either it's prime or what?
Or there's another few primes.
Or there's some more primes that make up this number that we didn't know about before. So any assumption that there's finitely many primes is wrong because we can directly construct a new number that must be divisible by more primes than the finitely many we have.
Yeah.
So that's cool. That proof is attributed to Euclid. So it goes back 2,000 years. This is a new proof, and what we're going to do, and this is really interesting, we're going to make a list of numbers, 0, 1, 2, 3, 4, and we're going to make a function that I think they call it f of n. And this function is going to produce a number 0, I don't know why I'm writing it like this, number 1, number 2, all the way down. And this is going to have 1 prime, and this is going to have greater than or equal to 2 primes, greater than or equal to 3 primes, when you factor it. And so we're going to explicitly construct a number so that at step n, it has greater than or equal to n plus 1 prime factors. So it's actually incredible. So you're actually just constructing a specific number in a finite number of steps, and it has greater than n plus 1 primes. And why would this show that there are infinitely many primes?
Because when this gets really big, you use bigger and bigger primes.
Okay? The number of primes you use
Yeah.
is bigger and bigger. And so if there were finitely many primes, let's say, what did you use, n? Capital N? Oh, actually I'm using n here.
We'll use m primes.
Okay, so there's only m primes. What's the problem that gets created here?
Well, when you get really, really big, you start using more than m primes.
Right, no matter what big number you pick, you're eventually going to get bigger just by counting by ones. Okay? All right, so let's see how this construction happens because it's really neat. Okay.
All right.